In previous videos, we've seen how we can use derivative information to get perspective on the shape of a graph. In this series of videos, we're going to introduce a new idea called Taylor polynomials that use derivative in a new way to get insight into a function as well, but also to construct a very specific approximation. This is not a new idea. Earlier, we've seen how to build linear approximations to a function. Imagine we had a function, and this could be a function that's quite volatile, not linear. If we picked a point on that function though, say a point here, called that coordinate a, then we could approximate that function at least nearby with f prime of a, remembering that that's a slope, the derivative at one point, and then we had a shifted linear function, so we focused our attention at a, or shifted to the right by a, and used the initial height, f of a, which is the coordinate at that point, and that whole construction built a tangent line, or linearization, or linear approximation. Those are all terms that mean the same thing. What we're going to do now is take that as a starting point and generalize it. We're going to give a label to this approximation we already have, because it is a polynomial. We're going to call it a polynomial of degree 1, approximating our function at a certain point. The general family we're going to be looking for is a family called Taylor polynomials. The fact that we're using degree 1 as a way to label this one here says we might be able to build a polynomial of degree 2 that would also have some of the same features of the linear approximation. Let's take a look. We're going to look at the graph of cos of x to start. And remember, the graph of cosine starts at the peak and then goes down at pi over 2 and has that shape there. Here we're going to look at the graphical interpretation first. If we added a tangent line at x equals 0, that's our x equals 0, we go up to the graph, we say what's the slope there? Well, the slope is pretty boring there, it's slope 0, and that would be our tangent line, or our linear approximation at the point x equals 0. Now we can see that that approximation's not bad, at least close by the point x equals 0, but very quickly the function deviates. And if I said this line approximates this function out here, you would look at me a bit skeptically. So let's take a note of that. This is a very limited approximation to this function. Could we just take one step further, introduce a slightly more complex form of a function that might work better as a fit or an approximation in this case? And again, with the clue from the last slide, what we could do is think, well, linear seems to be a bit limited. What would be the next step in one dimension anyway of something a little more complex? Well, let's make a quadratic approximation. And imagine fitting a parabola to this shape here. I don't know what it looked like exactly, but certainly it seems that a parabola could mesh nicely with the cosine curve. It won't go forever. The cosine curve eventually come back up, but it seems that a quadratic approximation would be a better approximation for longer than the simple linear or tangent line approximation. That leads us to our definition of a Taylor polynomial, now of degree 2. Fortunately, there's some really nice structure in this formula. Again, we're taking a function of any type and approximating it with a quadratic. Notice there's an x squared in here. But the really nice thing that we have is this first component here. If you close your eyes and ignore this term on the right, what we have here is our linear approximation. So we have the value of the function itself at the point. Notice this is a constant value a here, plus the slope times x minus a. What this is pointing out is that when we talk about the Taylor polynomial of degree 2, it's actually made up of the Taylor polynomial of degree 1 plus a new addition, one more term tacked on the end. That makes it easier for analysts and students to memorize this formula. Now, what is involved with this new term? It's a nice extension of what we saw before. We have a term with no derivatives, just about the value. Then we have a term with a slope and an x. And then we have a term with a second derivative and x squared. So there's a very nice continuous pattern here, and it ties back to the purpose of building this function here. But for now, it's enough to see what is in this new component, second derivative, x squared. There is one new ingredient you have to be careful of, and that's the scaling factor of 2. That's there for purely technical reasons so that this function on the right and the function that you started with have the same second derivative when you're done. But for now, it's enough to recognize the structure in this term here and how it relates to the earlier ones. So as a quick concept check-in, if you had values of x close to this point, this reference point we're starting at, and look at a and all the terms here, and notice where the x's are. There's only two x's here, the linear x and a quadratic x. Once you've built that function, which is just a quadratic in x, would you think this would be a better or worse approximation to the original function over here than a strict tangent line? And think about why. We'll give you a moment to answer that, then we'll check in. All right. The answer in every case, in fact, will be that the quadratic approximation will be a better approximation than the linear. And you can see why. If this information from the linear approximation is already in the quadratic, we have all this, and then we're adding some more detail. So if before we could capture the slope of the function, we're always going to get more information if we capture the concavity or the second derivative information as well. So we're not going to be able to lose anything because we have the linear already included, and by adding the quadratic, we're going to add more information for sure. And so that indicates that this quadratic approximation should be a better approximation than just a linear one. It's a little more complicated. It involves a little more work. We need the second derivative computed at a point, but it should give us a richer approximation, a more detailed approximation to the original function. In the following videos, we'll apply this to specific examples.